They do not run. They ski on their skis.
My mom
You know
is
the combo, if you're looking at the comic book, it's line and it's like right in the spring.
a good workout.
But imagine it's hot. So you're on.
All right, let's take a look. Okay, I want to run you through a couple quick problems here, kind of get you thinking about optimization again. One of these is I like this one. This is pretty typical college calculus project you'd see in any calculus class, first semester calculus class. It depends on setting up a good picture. That's what I like about this. And there's one very similar to this on the second assignment too that I'll let you work on your own. What are we going to do here? Find the volume of the largest right circular cone that can be inscribed in a sphere of radius r. So suggestions for the picture.
We draw a sphere.
Okay, draw a sphere. Okay, spheres are hard, but circles are pretty easy. So actually, circles are really easy for me because I can cheat.
Yeah, exactly. Oh, that looks pretty good.
Okay, so yeah, now drawing this is a three-dimensional problem, isn't it? But really all of the reason we're drawing the picture mainly is to find a place to identify our variables and find relationships among the variables. All the variables that we need here are going to be, we're going to get from just a two-dimensional cross-section right down the middle of this sphere. So let's do that. Let's Yeah, aren't these nice?
Yeah.
Okay, so there's our cross section of our cone. Anybody know top of their head what the volume of a right circular cone is? 1/3. Yeah, that's right.
Pi.
Volume is 1/3 pi
R squared H.
r squared h. That's it. Good.
Nice.
Now, being as they use as r is the symbol that we're dedicating to the radius of the sphere, I'm not going to use r. Well, that's the formula. But how about if we call it something a little different, and we'll use the variable in our picture too. So what if we call it like x squared y, something like that? And if we do that, isn't this distance right here then x,
Wait, what?
I guess.
right?
The whole thing or just where the line is?
Just that line right there, just that little bit right there would be x.
Right.
Because that's the radius of the cone,
Oh, because it's like that.
right? And this is just a,
Oh,
does that make sense?
yeah.
Okay. If I did draw that cone three-dimensionally, there's that segment right there, isn't it? Does that make sense?
Yeah.
Okay, and then y would just be this guy right here, wouldn't it?
Here it is.
Yeah.
Not the best drawing.
Does that make sense?
Yeah.
Okay. And then r, of course, is the radius of the sphere. Now, is r a variable?
No.
No, it's not. We're going to treat it like a constant, aren't we? Because it's what's containing and constraining our cone, right? Without the sphere enclosing it, encapsulating it, if we wanted to find the largest right circular cone, we just make it infinitely big, right? That's going to be, it must be the constraint though, it must be related to r, right? Because that's what's containing this thing. Well, that is our primary equation right there, isn't it? That's what we're trying to maximize. What's the problem?
We need a
Two variables, yeah. Yeah, we need a secondary equation, which must be the constraint, which must be related to that, because that's what's constraining the cone, right? Okay, so suggestions. Any ideas?
Let's see. Volume of the sphere.
Should I draw the radius of the sphere?
Yes.
Okay, so that's just gonna go from the center, which would be right about there, I guess, huh? Now, any particular radius that you would suggest I would draw?
Well, to the top.
To the top, okay, that's a good one. So there's one of them, that's R. Okay. What else? I got to somehow come up with the relationships between X and Y and R, right? So I can solve for X in terms of Y or vice versa.
Pythagorean theorem.
Say it again.
Pythagorean theorem.
Pythagorean theorem is a pretty good suggestion. Now, where am I going to get a Pythagorean theorem? That is a right angle, isn't it? Ah, okay, so between the center and like right there? Yeah, okay. Oh, what if I did that? Good, good. Okay, what are you going to do with that? Now, you know this is R, don't you? This is R. So there's one side of that right triangle. One side is X. What's the third side? Y minus R. Everybody see that? Good, because the Y is the whole height of the cone, and R is just this portion from from here up to the top. And so what's left over must just be Y minus R. Let's make that green. How about? So this we know that this green segment is Y minus R. And now we've got all three sides of a right triangle, so we should be able to just use Pythagorean theorem to relate those variables. Okay, so then for our secondary equation, we get what? R squared equals X squared plus the quantity Y minus R squared.
Yes.
Okay, suggestions about our substitution, and which one should we isolate here? Think about this a little bit. And remember, our goal isn't necessarily to solve for a variable. Our goal is to be able to get rid of a variable from the top equation. I want to do it as easily as possible. My goal is just to get rid of the x's in favor of y's or vice versa in that top equation, primary equation. X squared, yeah. Look at that. See, we've got an x squared right there and an x squared right there that would be easy to isolate, right? So just solve for x squared, and then that's going to be a real easy substitution. So then our substitution equation would just become x squared equals r squared minus the quantity y minus r squared. That make sense? Which we could simplify a little bit. If we square this out, what's that going to be? Minus y squared.
Yeah.
If I FOIL that out, expand
2yr.
2yr. Good. Minus 2yr plus r squared. That's what I'm subtracting. So then if I subtract all that stuff, the r squareds go away, right? Does that make sense? And I just end up with
I did for a minute.
x squared equals positive 2yr, or probably should say 2ry, minus y squared. Make sense? Okay, we'll plug that in. There. And what are we left with? Let's see, then we get d equals pi over 3 times y times that whole thing, right? Times that expression. So now it's d of y. Okay, and we can just do our calculus, right? While we're at it real quick, what's our domain? And I probably want to distribute that y, I guess, don't I? So we don't have to do the product rule.
Yeah, that makes sense.
So,
Wow, it's rich, right?
times 2 ry squared minus y cubed. what is our domain? And we can do this from the picture and or from the function. So if y is our independent variable, what would be the smallest value of y that we would want to consider?
0, slightly above 0.
I mean, we could make y go clear up here, but is it going to make any? If you think about the formula for the volume of a right circular cone, it depends on the radius and the height, right? Wouldn't you agree that if I did something like that triangle and that cone and that cone each have the same radius,
Yes.
but this one has a much bigger height, agreed? So would you ever want to choose a height that would be less than the radius of the sphere? No, it's going to give you the same radius for the cone as a much bigger, right? I mean, it would make no sense, would it? So we could logically, not mathematically, but we could logically.
Okay, I have a question.
Yeah.
How do they have the same radius? Because if they have a different spot, wouldn't it be a different spot on the
Those
screen?
two cones?
Yeah.
Well, because look, these two, I mean, like, what if I drew them, if I superimposed them so they look like this? See, those are vertical lines?
Yeah.
And so the radius of these cones, there and there, would be the same,
Oh,
right?
because
Oh.
Does that make
just
sense?
those two randomly? Okay.
And so, what I'm saying is that those would be symmetrical about that midline,
Yeah.
wouldn't they?
Yeah.
If I go up a certain amount or down a certain amount
Oh,
from the
okay,
equator
okay.
of the
I
sphere.
thought you meant like all of them had the same radius.
Oh, no, I got you,
Okay.
okay, yeah. Right, so my point is, we would never use that top one, we'd only use the
Yeah.
bottom one, because that's the same radius but a bigger height,
Yeah.
right? So we'd only really wanna look, and that was probably kind of a clumsy way of me saying that, but we only really wanna look for values of y that would be greater than r, right? R being the radius of
Yeah.
the sphere.
Yeah.
Does that make sense?
Yeah.
So the lower limit of our domain would just be r, right?
Alright.
Okay, so what's the upper limit? And kind of think what these would do, and it really helps to kind of just play a little cartoon in your head here. If I were to take these things, if I took these points and drew them up here, I'm gonna get kind of a shorter, wider cone. If I draw the points of the triangle down here three-dimensionally, I'm just creating a taller, skinnier cone. What's the limit of that? 2r, yeah. And when I get to 2r, I mean, it's debatable. I guess mathematically we could keep that, couldn't we? But is that going to give us?
No.
No, it's going to give us zero volume anyway, isn't it? So whether you make that rounded or square is really irrelevant. It's going to be it's a point that's not going to maximize volume anyway. But that's our domain. We're only looking for values between r and 2r for the height of this thing, right?
Okay.
That make sense? Because if we geometrically, the height is y. As y increases, the very biggest it could get would be if it was so tall and skinny that the base shrunk to 0. See what I'm saying?
Yeah, I got you.
Okay.
Makes sense. Yeah, I got you.
All right. So, questions? Does that make sense? And it's, we could come up with these relationships mathematically, but it's a lot easier just to look at the picture, I think. You just kind of think about the extremes of the picture, right? As you know that as y is going to get real big, then r is going to or x is going to have to shrink.
Yeah.
Does that make sense? So as x goes to 0, y would go to 2r. Okay? All right, so now we're really to a point where we can just kind of do calculus. This becomes, we've taken the picture out of it for now, right? We use the picture to, in the situation, to build our primary equation in a single variable. We got our domain, but now we're just going to differentiate, find critical numbers, make our table, take it from there. So let's do that. Let's grab all this stuff down here, and we'll go to a clean page and just do the calculus. Okay, so then here's the function we're gonna differentiate. What's the first derivative?
Oh, boy.
That's probably the easiest
Oh, yeah,
place to differentiate right there. We got the pi thirds out front, just a polynomial, isn't it?
yes.
What are we gonna get?
4
For our Y.
Okay.
That's a prime.
And I'll just put that pi thirds out front. So I'm gonna get 4 r y. Don't we need the product rule there?
Yeah.
Do we?
Oh, no, because R is not a variable. That's
Ah,
right.
good. R is not a variable. R is kind of, it's sort of a hybrid almost, what we call a parameter. During the, it's weird to think about because we didn't specify R, did we?
No.
So in our answer, we're gonna get R's in our answer, and then we could go back, in hindsight and say, well, yeah, what if R was 20? What if it was 100? And we could just plug that in and get values in terms of R, right? Of whatever R we chose. But it's not really a variable because R can't change within the context of the problem, right? The sphere can't shrink and grow while we're changing our, the cone. Does that make sense?
Yeah.
We're saying that for a fixed R, whatever, if we're gonna decide on what R is gonna be and it's gonna stay constant, we're gonna tweak the cone inside the sphere. So R is not a constant as far as the calculus is concerned. Does that make sense what I'm saying there? Because that's a pretty big deal in calculus, right? And that comes from this language here, inscribed in a sphere of radius R. So the R is given and fixed. So there's what we get from the first term. What about the second term?
3y squared.
Okay. And so there's first derivative. We can find critical numbers pretty easy for that one. V prime equals 0 when what? What's the part that we would say it equals 0 when we solve here? Yeah, it's just going to be this part right here, isn't it? Right. So we'd say when negative 3y squared plus 4ry equals 0, how would we solve that equation?
Factor out a y.
Factor out a y. Good, I'm going to factor out a negative y, leaving us with 3y minus 4r. And so what are my zeros?
0.
Okay, so either y equals 0 or y equals,
4r would be.
yeah, 4/3 r. Right away, which one of those do you think is probably going to end up being our solution? 4/3 r, yeah. Okay. Okay, now, do we want to take a second derivative here?
I would.
Okay,
Question, yeah.
I'm sorry. So why is R constant again?
Okay, R's a constant because if you go back to this picture, see this statement right here, it's inscribed in a sphere of radius R. So that might as well have been 10 or 100 or 25 or something, right? But to make this more general, we're just gonna call it R. So it could be anything, but it can't be changing during the problem, because that wouldn't make sense, would it? If we're trying to use calculus to maximize this volume, if the sphere were changing as we were morphing this and making like X smaller and Y bigger, that's cheating. That's right, don't you think?
Yeah.
I mean, that's not gonna give us, we're not solving a legitimate calculus problem then if the sphere is changing also. The sphere has to be fixed radius R, but because we never specified what it was, we could plug in any number at the end that we want to.
Okay.
But it still has to be treated as a constant. Really, like I said, it's what we call a parameter.
Okay.
Okay, it's something that's, it's fixed during the problem, but then we could go back and assign it any value we want to.
All right.
Does that make sense? It's a little weird at first, I know, when you think about that, but it's really not a variable, okay?
Thank you.
Mhm.
Loco? Oh, that's crazy.
Okay, so do we want a second derivative here? I'd say there's a definite answer on that, in my opinion.
Oh, I say yes, let's do it.
How come? You're right.
Because it's easy.
It's easy. It's a polynomial. It's easy to do, and the second derivative test is easier than the first derivative test.
Oh, yeah.
So we might as well go second derivative, and it's gonna be what, pi thirds times and we can make our table.
Yeah.
Okay, so y is our variable in y. Okay, and we said, didn't we say we were gonna go from
R to 2R.
R to 2R? There we go. Okay, and we got two critical numbers. We got 0 and 4/3 R. Well, 0's not even in our
No.
domain, is it?
Yeah.
Right.
I guess
So 4/3 R was a 0 of the first derivative. Okay, here's where that second derivative really pays off then. If I plug in 4/3 R into the second derivative, is it gonna give me back a positive or a negative result? And all we're really looking at is right here, aren't we?
Yeah.
4R minus 6 times 4/3 would be, what's that gonna be, 8? Right, so clearly gonna be 4R minus 8R negative. So that's negative, and so we have a horizontal tangent and it's negative, so it's sad function, so it's a maximum, like we wanted. And they just wanted dimensions, didn't they? Right, so we know what y is, we don't even really care what the volume is, they don't ask about the volume, they just want to know dimensions. So we know that the radius is, or excuse me, the height of the cone is 4/3 R. Where do we go to find the radius?
We are looking for the volume.
Oh, we are looking for the volume?
Yeah.
Okay, well, if we do want to find the volume, where do we go to find the volume?
Initially.
Yeah, we just go right back there. We've already got the volume solved for a single variable, so take advantage of that. Just plug it in, you know, really either one of those, probably right here. Right?
Yeah.
And we won't even do that. You can do that. Right? That's just a matter of plugging in a number for y, simplifying.
So,
But you guys, you're good. You can do that on this one. What if we want the dimensions though? What if they did ask for the dimensions? Where would I go to find the dimensions? To find the other dimension. We know what y is in terms of r. Right there, right? This gives us x squared, so I would just square root that number that I get. Right, we always go back to our substitution equation to get the other variable. Okay, does that make sense?
absolutely. it
Okay.
does. Yes.
All right.
Yeah,
We out of here.
Until
The
it's on
2 minutes.
30.
Oh, okay, never mind. Short period. I was gonna do one more. There's one other one I want to do at some point, but I think